Hi everyone, thanks for joining. Before we get started, if you'd like to ask a question at any point during the webinar, you can enter it in the webinar control panel. We'll then answer all your questions at the end of the webinar. So without further ado, I'll hand you over to Nick.
Hey, thanks a lot, Tom. I appreciate it. Hello, my name is Nick Ronconi from Applied Tech Systems. I want to thank you all for attending today. The focus of the webinar are possible solutions for two issues that many OEMs and suppliers are facing today. As manufacturers continually drive lot sizes to smaller quantities, companies are facing increased documentation and traceability requirements. In order to respond to quality issues, the question becomes, how do I serialize and mark my parts and assemblies? And then how do I digitize my quality data and trace that data back to the individual unit level? This is especially challenging in metal fab and assembly processes where metal parts are difficult to mark, and both parts and assemblies may go through welding, painting, or other processes that have harsh environments. So we're going to start today with Doug Stubbs from the Schreiner ProTech company, who will provide an overview of innovative labeling solutions for metal fab and assembly operations. After that, I'll give a brief demonstration of software that's in use in many plants for recording and reporting out on your quality data. So at the end of today's meeting, we'll have some time for questions, and we'll also be sending out, as Tom said, some follow-up documentation to all attendees. So with that, I'll turn the presentation over to Doug Stubbs.
If you'll pass me the screen, please, away we go.
All right, you should have it.
Perfect, very good. Can you see that, Nick? All good?
I can.
Terrific, very good. All right, good morning, everyone. Thank you for your time. We've got about 27 minutes that are going to go by very quickly. What I'm going to review this morning is a few moments on individually marking and tracing of individual pieces throughout the entire application and production process here. So as all of us know, the requirements of individually tracing and identifying parts throughout manufacturing processes are growing exponentially nowadays here. What used to be just having to keep track of a part at the end of your process and out the door is now radically different. You're required to track that part from the moment it arrives on your dock through every step of the manufacturing processes and then out the door as well. This now includes processes which were excluded in prior days that were difficult, where technologies had not yet developed to allow you to track them through these individual places. There are unique challenges with both of the materials that are used in typical assembly applications, in particular plastics and metals here. So there are three real common technologies available for individually marking for assembly applications. The first and most simple, of course, is traditional labels. Traditional labels have had their difficulties in some applications because of the primary challenges of adhesion, abrasion, and contaminants or chemicals. In particular, the ability to keep the label onto a particular substrate is dependent upon the material itself, as well as the adhesive that is selected. There are a lot of very good, huge adhesives companies now that can create formulations to stick practically any label type material onto virtually every surface as well. In terms of abrasion, that has always been challenging, particularly in assembly applications where the parts can be very bulky and not individually packaged, and therefore they can be scraping and bumping against each other throughout the entire process. So any label that is exposed must be able to handle this kind of jostling around and potential abrasion as well. And then the most challenging can be the influence of contaminants or chemicals. Chemicals in particular can be very challenging for labels because they can attack and degrade the adhesive. They can attack and deform the material or the paper-like material of the label itself. And even after a label is printed, the ink that is on the label can be compromised with the right mixture of chemicals in typical processes as well. So one of the primary methods to protect a traditional label is the use of a protective mask here. Individual masks have been around for decades here. They're basically a removable overlay that is a protective wrapper for the actual label itself here. When constructed correctly, they are both chemical and process / abrasion resistant here. They protect the entire label until the time of your choosing when you wish to remove the mask itself. They are typically not very costly solution to this, and they are exceptionally used in many applications throughout these kinds of processes here. If you have not seen what a label with a mask looks like, here's about 20 seconds to give you an idea here. So these are individual labels that have been printed. They have the protective mask on it. They are going to, in this case, be painted, but the concept does not mean you have to paint them, but any type of coating that would go over the label. After curing, the labels can be the mask can be removed, peeled away, exposing a pristine label with all of the content as you had planned on it before. A second technology that is very common but not well known is the use of laser etchable films here. These laser films are extremely uber rugged, adhesive back traditional type labels just made of a very special types of materials here. They are extremely resistant to chemicals, extremely good against abrasion as well. They can work at very high temperatures, very low temperatures, and they are an alternative typically to direct laser marking on the parts themselves, and they use standard industrial lasers. If you haven't seen what these lasers are capable of and how this kind of a material is marked, this is actual speed here. Just like these kinds of lasers are used to direct mark onto parts themselves, you can use this same technology and make removable labels at extraordinarily speeds out of very, very durable type materials. Okay, there are two primary types of these laser etchable films. The most common is known as an ablation film. Ablating an actual material is where you use the laser to burn off a top layer and expose, in this case, a different color second layer beneath it here. In the video we just saw, it was a black material and it was then exposing the white underneath it here. Ablation films are exceptionally common here. However, when they burn away that top layer, those fumes have to go somewhere in that material. So you typically have to have an air reclamation system to keep those fumes away from workers as well. A second option, very similar in construction, is known as a color laser film. The primary difference of a color laser film is that it has a top layer, a top laminate that seals in the layers beneath it here. When the laser writes or cuts, or when the laser prints through that top laminate, it does not damage that laminate. It simply passes through it and then pushes away the black material to expose the white underneath it here. Primary benefit of that is there's no smoke that's generated during the printing process because all of the black material is sealed in, keeping the resulting in a no fume type application here as well. And this particular product, these are available with optional paint masks or protection masks that we looked at previously too. The third technology for tracking individual parts is the use of RFID. As most people know, RFID is by far the fastest growing technology used for individual tracking, tracing, and identifying of individual parts here. It is a remote data capture technology where you don't look at a label, it's simply scanned and recorded up into the software and your overall MES system. For RFID labels or to be used on individual parts, there are two primary form factors of the receiver or the part that goes onto the actual part itself here. One is traditional labels, just like we just discussed. You put the electronics inside of a label type of construction with adhesive on it, and then apply that label onto the actual individual part here. This is exceptionally common here. The second common form factor is RFID tags. Tags come in many different form factors, sizes, shapes. They are exceptionally durable. They can be, if made out of the right materials. They are typically mechanically attached via a fastener or a strap or something similar to bond it onto the part, either temporarily or permanently here. So when we look at using either of these RFID form factors onto either plastic or metal surfaces, they are absolutely both viable options for tracking these kinds of parts. Labels themselves with the adhesive backing, you have, in terms of the adhesion, the same considerations that you do with just applying a regular label. In terms of abrasion and chemical resistance, you can also have, in many instances, the protective masks put over standard labels as well as RFID labels. Comparing that with the RFID tags in their various form factors, their adhesion is not necessarily a consideration unless you have an adhesive backed tag. And then in terms of abrasion and chemical resistance, those form factors are very unique and exceptional in being tolerant of difficult environments here. So if we take a peek at, in summary, these three different technologies and what are available, traditional labels are, of course, the most simple, lowest cost, easy to implement here. The laser engravable labels are a step up in terms of their ability to adhere or resist chemicals and abrasion, exceptionally durable. And then the RFID product lines on the far right-hand side, depending on the form factor chosen, offer the various options. The primary enormous benefit of RFID is that it allows you to have automatic transfer of the data and tracking of those parts directly up into your system without physically looking at the label itself. So next, I'll pass it back over to Nick, where he will talk about what you can do with this actual information now that you've got it available off of the individual parts. Nick?
All right, thanks, Doug. Definitely not your father's labels, I guess I would say. A lot of versatility there. So you should be seeing my PowerPoint slide, is that correct?
Yes.
Very good. All right. So once you've marked your products using one of the methods that Doug spoke about, you now have the ability to identify that product throughout your processes. Now, this is especially important when you're collecting quality-related data, whether you're stamping, welding, assembling with adhesives, or similar processes. Every product flow has quality gates established where inspections and repairs take place. So as Doug pointed out, it's not just typically a final assembly station anymore. Due to the small lot sizes and the need to respond very quickly, there are multiple quality gates with multiple types of inspections, as you see here, that typically take place throughout a process. So there usually is a final inspection, but there are usually other types of inspections that you see listed here, like dock audits, layered audits, audits when one fabrication area releases components to another area, etc. So if you're collecting that information now, it's probably being done on sheets that look similar to this. So there's generally two form factors that an inspection process takes place on. One, if you look in the upper right-hand side of this, is a sheet that lists an image of the product, and an inspector notes defects and defect locations against that image so that your tooling people have an actual idea of not only what defects are occurring, but where they're occurring. The other type of interface or paper form that's used is what we would call a checklist. There are many forms of this. I have two listed on the left-hand side of my slide here. One is a good example of a non-destructive weld audit, where an inspector would be presented with a list or a diagram of various welds, and then they have various types of defects to choose from. And if they see any of those types of defects, they'll mark them on the form. If you look in the lower left-hand side of the slide, you'll see what is typically called a start of run production check sheet. When a job or piece of equipment is set up or a changeover takes place, generally there are various criteria that an inspector verifies to make sure that the job is going to run correctly. Those can be measurements, they can be visual verifications, etc. So if you're using pencil and paper to collect this data now, that's typically problematic in the sense that, number one, there's always a lag time from when that data is taken from the paper format and put into an electronic format, such as an Excel spreadsheet. And B, well, you now have a lot of defective material built up in your WIP, so you have to do sorting and other things if you fail to catch a problem due to the non-real-time nature of paper and pencil. So another alternative to paper and pencil is a software package that replaces those paper forms. What you should be seeing now is a screen that is an example of our Inspect Data Collect software. Data Collect is software that runs on either a tablet or a fixed station PC, and it replaces those paper forms. And when you're collecting data, all that data is immediately placed in a database, and it's available for reporting and analysis and notification purposes. So the first step in any inspection process is saying, what am I inspecting? So you should be seeing now a pick from list. And this is one way to check a product, or select a product, I should say. I'm going to start with a fabrication example where we're checking a fender, and then I'm going to move on to an assembly type of an inspection process. You'll notice that when I scan the barcode on the fender, there's a field in the software up here at the top, and it captures that serial number. So I can also key it in, but as Doug pointed out, these days it's much less error prone and it's easy to mark your parts with something like a barcode or an RFID label. You can also scan and capture child part relationships. So if you have an assembled product, let's say an automobile, you can scan the VIN number and then you can scan the label on, say, an airbag, and then you have full traceability as to what airbag has been installed in that end unit serial number. So first we're going to do a sheet metal inspection of a fender. So you're looking at a image of the fender. You'll also see some tabs and such across the top. These tabs are used for navigation. I just want to mention that this is an off-the-shelf configurable package. So you can add and remove tabs. You can change the size of buttons and windows. You can rename things. So in all cases, the end user is taking an out-of-the-box product and they're customizing it to meet the takt time requirements of their inspection processes. So moving forward with first a visual inspection, let's say I see a dent on the sheet metal. I simply touch or click on the location and Inspect captures that location. Your inspector is then presented with a list of defects that are specific to that component and that quality gate in your process. So here in a simple type of an application, I'm just going to select the type of defect, in this case a dent. I'm going to say I'm done, and the software now knows both the location and the type of defect. You'll see a flag and a lead line going to the image of that part. I'd also like to point out this is a live CAD image, so I can rotate it. We also have the concept of thumbnails, which you see over on the right-hand side, and by clicking on a thumbnail, it will change the orientation of your CAD image to a predefined zoom level and orientation, so you can place the defect exactly where you see it on the part. So you can place multiple defects on the part. It's very fast. You can see here, I'm just going to place 2 or 3 defects, and you can see how simple that is. So at any point in time, if you look over on the left-hand side of your screen, you can also see that we can make electronic versions of job aids, work instructions, etc., available to your inspectors. So I can have more than one. These can be videos, they can be photos, they can be PDFs or Word documents. You can also send quality alerts to the floor. So if you have a known issue, instead of printing out sheets of paper and hanging them at your stations, you can immediately make your inspectors aware of a quality issue that they need to take note of. So that was a simple example of collecting defects in a visual manner on a stamped component. But now let me move to an assembly. So what I'm going to do here is I'm going to imagine that I am creating or assembling fire trucks. Now I'm also using this example because I want to show that you don't have to use a CAD image. In a second, you're going to see multiple photos being brought up, and you can also use photos if you don't have access to your customer's CAD images, etc., in order to use them for inspection. So similar to the thumbnails, what you're going to see here are multiple photos. Each photo represents a different view, and just like clicking on the thumbnails with a cat image, here I'm just selecting which image I need to have presented to me in order to log the defect type. Now, when you're assembling a product, there are multiple components that go into that assembly. You'll notice here, if I see a defect on this ladder, I click on it. The software knows what component that was, in this case, a wooden ladder. So it only presents to me defects that are associated with a wooden ladder. So in this case, I'm going to pick splintering. You'll notice if I click on the wheel cover or hubcap, I get a completely different set of listing that is specific to a hubcap. So if I note that there are dings, that might be the end of it. But many times there is additional information that an inspector wants to note regarding a defect on a particular component. So in this case, many people rank their defects. So I'm going to say this is a minor defect. We also have the concept of assigning a responsible cell and area. Why would you want that? Well, here, if I am doing a final inspection and I see a dent in the wheel cover, well, that may be a product of the stamping area. In other words, I found it at assembly, but it's really a stamping issue. So I can select both a responsible area and a responsible cell, and that will also be associated with the defect, and I can sort by that later. Date stamped, and it's associated with that defect on that component on that serial number. All right. Can people hear me or not at this point?
Sorry, Nick, you dropped out for a second there, but you are back now.
Okay, sounds good. Sorry about that, Tom. All right. So what I'm going to do is save that defect on this record, and now you've had an example of visual defect entry on both an assembly and a fabricated part. The other type of interface we spoke about is a checklist. A checklist interface is exactly what it sounds like. You have a list of quote unquote questions that you would like your inspector to go through at a given station. So here I have a list of specific questions for this model fire truck at this station. These questions can be answered via multiple choice. So I can confirm option content, for example. So here, if I'm supposed to have a chrome bell, I say it's chrome. That is the quote unquote correct answer. And now I'm going to take a couple of measurements. So for example, here I'm supposed to take a paint thickness check on the hood. And I see a job aid has appeared over here on the left, which just like during the visual inspection, I can access and enlarge. Now, the software knows what the correct answer is per se to a question. So if I take a value, the software compares that value to the spec limits. If it's in spec as it was here, it goes on to the next question and it displays a green check mark. If I go to questions here, like I'll just jump to this badge placement. If I have a job aid and it says, hey, this is what the badge placement is supposed to look like, is that what it looks like? And I say no, the software knows that that is a wrong answer and it enters that as a non-conformance in my inspection task for that product. So the last thing I'm going to show you here is via the ability to enter in a checklist set of questions and enter defects against a visual of the product, you can handle almost any inspection task at your facility, whether you're assembling or fabricating. But the last thing I want to show you is generally if there are defects on a part, your work in process is routed to some kind of repair loop or repair cell, or sometimes it can be fixed in process. So the software also allows me to click on this hammer and wrench, and now the software is in repair mode. So now your repair person can see every defect on the part, they can select that defect, and now I can access a list of repairs that are specific to that type of defect on that part. So here I'm going to replace the ladder. You'll notice that the flag turns green. And now I have noted that that has been repaired. Or here it's, yeah, there you go. Now it turns green. So that's a good example of both checklist and visual defect entry. As I mentioned before, all the data, when I'm collecting it electronically, is immediately transferred to an MS SQL database, and we have a web-based reporting package. So the interface for the reporting displays all of the reports available, and there's 70 to 80 of those on the left-hand side. First, I select the type of report I want, and then on the right-hand side, you can see that there are various sortation criteria that I can use to filter the data used to populate the report. I can put in a particular serial number, I can sort by shift, time and date, cell, model. There's a myriad of ways I can filter the data. Now, Doug talked a lot about tracing your parts by adding barcodes or RFID tags to them. Well, if you are having that unit move through the process and you're collecting that information as you enter the quality data, now the software will put all of that data together in what might be called a digital thread or record of everything that happened to that unit. So here, let's say I have a dealer for my fire trucks or some hoods I produced, excuse me, say that, hey, we have a problem with this serial number 56875. Well, I can run the report for that serial number, and now I'm getting a record that compiles all of the information that's been entered at all those inspection points on, in this case, a hood. So you'll see at the top, it has the part number, it has the serial number. There are other ID fields available for things like airbags or other child components you want to tie to that parent component. As I scroll down, you'll see that this hood has been inspected in 2 areas. I can see how long it took each inspection to take, what shift it's on, who the operator was, what station it was collected at, how many defects there were or repairs during each inspection, and other information. As I scroll down here, I see an image of the hood. It notes the locations of the 3 defects that were found. The green marker indicates that that defect has been repaired. The red marker indicates that that defect has not been repaired and is still open. You can get more information of each one of those 3 defects. Here, for example, on this dent, I can see the comment by the inspector is that there's new material handling that might be producing those dents. You'll also see over here in the image column on the far right, I see a 1 which tells me that I can click on that because there's an image of the defect that has been attached to that record and that defect on that unit. So as I scroll down even more, the record concludes with any checklist questions I had. In this example, I've answered 5 checklist questions and 1 of them had a non-conforming answer. So every unit, as it goes through my processes and my quality gates, will allow me to get a record of everything that happened to that unit. But then since all of the units are tied together in a database, I can then get aggregate reports. So I've pre-run some report here for time savings purposes, but you can access reports on a real-time basis, such as, hey, for a certain time and date range, certain model, certain part number, what are the major defects that I'm seeing? So you can see here that scratches are my biggest problem. You can go with this a different way. If you're making multiple products or assemblies, you can say which product or assembly is producing the most defects. So here I can see for whatever time and date range or shift or whatever that I've retrieved data for, that I'm not going to spend much time on trying to figure out why I have a problem with the fire logo. I want to see what's going on with the fire truck body. The software is very powerful. I can sort my defects by shift or hour. Here you can see that in terms of overspray in my paint department, that hour 4 for some reason is producing a lot of overspray, where hour 3 is producing the bulk of my porosity. So this gives me actionable information that I can use to put in place some corrective actions. When I do that, you can then use the software to get reports such as concern trends, first-time yield reports, etc., that tell you whether or not you're getting better or worse. What I'd like to finish with is one of the most powerful reports, which is what we call defect mapping capability. So remember, we're capturing both the location and the type of defect. So not only can I get a record and a map of defects on a single image, but the software can lay multiple inspection records over each other on that CAD or stock image, and I can get reports like this, which map all of my different defects against my product. Over here on the right, you can see that we've assigned a different icon to each type of defect. I can map all defects, or I can pick just a particular defect, such as a scratch in this example, and I can map those as they occur on multiple records, and they're all mapped on one image. This gives me real powerful information to go back and make tooling and material and process changes. This is a live CAD image. As we talked about before, you can rotate the CAD image as I'm doing here. All right, so that's a quick review of the, of the data collection and the reporting. I'm now going to open up the floor to questions and answers. You do have a chat box, so if you'll just type your question in that chat box, Tom will read off the question, and then based on the question, Doug or I will answer it. So while Tom does that, I'd like to thank you all again for attending. As I mentioned earlier, we'll be sending out information that is a follow-up to this. And then if you have any applications you'd like to discuss at your operation, please feel free to reach out to us. Thank you.
Thanks, Nick. Thanks, Doug. So we do have two questions. First one is, why would anyone laser etch a label instead of marking directly on the part?
Yeah, that's a super common question here. There are a couple of primary use cases in that instance. The first is if that part is going to be painted or coated after the etching were to occur, it can be difficult. You know, a colored paint, of course, would obscure the marking entirely, but if you have a label with particularly a paint mask on it, you can then preserve it and be ready to go after that step. Another prominent use case is that not every material is suitable for direct part marketing. For example, if you have a black plastic material and it only lasers up to a gray, you may not get the contrast you need for a black-white type of marking. And then finally, labels give you flexibility of branding with different colors. So the ones that we showed in the videos and in my presentation were black and white only. There's any number of different color combinations that are possible. You can't typically inject a blue into a metal part or make a particular plastic turn green, but you can do that with a laser etchable label.
All right, thanks, Doug. And next we have, is it possible to interface the Inspect software with other systems such as SAP?
Yes, good question. So Inspect can certainly run as a standalone application, as it has its own database and its own reporting, so you can use it standalone. But based on that question, generally people do want to get data from our software into other applications, typically ERP or MES type systems like SAP, Plex, etc. So because the data is in an MS SQL database and because the software also offers a communications module, you easily have the ability to pass information in a variety of means such as OPC, text file outputs, etc., and decide what information you would like to either pass to an ERP or MES system. Or I would also like to mention on the input side, we often interface automated test and inspection equipment such as vision systems, wheel alignment machines, leak testers, X-ray machines, things along this line to our software for data entry. So yes, you can interface this software on the back end to send information to other systems for reporting in those systems, or we can do some integration to integrate inspection systems that enter data on an automated basis. Thanks, Tom.
Great, thanks, Nick. And that's all the questions for now. So if you do have any further questions, feel free to get in touch with Nick or Doug. And all that's left to say is thanks for attending, and we'll see you next time.